The next presentation will be given by Dr. Frank Freedman, who has several activities, consulting, teaching at universities, and has been working with our company for more than 20 years, I believe. And you will find the description of his capability and his CV in this web page. The title is Fire Plume Modeling. And Frank, I'm going to stop the share, and you can share your slides.
Okay. Well, thank you, Paolo, and thank you all for attending. It's always nice to participate in these classes that Wessex organizes and Paolo leads. So let's get started. So hopefully you all see like my screen, my computer desktop here, and I'll then shoot over to the presentation slides now. And is my voice coming over loud and clear?
Yes, loud and clear.
Good. Okay. And let me know if it fades out. I sometimes have issues with the microphone on my computer here. So yes, as Paolo mentioned, the title of the presentation is Fire Plume Modeling. And my name is Frank Freedman. Like Paolo mentioned, I have worked with EnviroComp for over 20 years doing a range of modeling and meteorological and dispersion analyses. I also am associated with San Jose State University, Department of Meteorology. I've been there for many years doing various things. I've taught air pollution for many years there. I've stopped teaching air pollution, but I'm currently working as a researcher there on projects that relate to fire. So the background I have in fire is a combination of the current work at San Jose State I'm doing, plus a lot of the projects that I've worked on with Paolo that have involved dispersion from industrial fires, which is what we will talk about in detail today. So this picture here is a comparison of the kinds of plumes that can be modeled with dispersion models, and particularly with fires. On the right is a large industrial fire plume that you can see has very distinct visual differences compared to the photograph on the left, which is a plume from an industrial smokestack, a typical kind of photo of that. And just the easy visual comparisons, that differences that can be gleaned from this, and some similarities. Well, the similarities is that, yes, you have an emission from a particular source where there's a flux of mass in the form of air and a small amount of particulate ejected out from a source with some type of volumetric flow outwards. And then eventually the momentum from the ejection gets detrained into the ambient air, and the plume then advects normally with the wind after that point. Well, the same thing happens with in a large industrial fire, except the fact that there's so much heat and mass from a fire is that it takes a long time, oftentimes, for the heat and the mass ejected from the fire to be detrained into the air and lose its momentum. So much so that in some cases, as you see on this photograph on the right, the fire plume can eject well above into the atmosphere above the planetary boundary layer top. And that this kind of anvil shape is an indication of the plume ejected above the planetary boundary layer and then kind of going off in unpredictable directions at that point. So the mass amount of heat and mass from a fire is different from an ambient, a Gaussian plume, from a smokestack. And that can lead to very different considerations when you attempt to model the fire versus the typical plumes. And that's what we'll talk about in more detail in this presentation. So the talk outline, first we'll go through some background of fires and show a few more photos and diagrams of fires to kind of explore these aspects in more detail. Then we'll go into some fire modeling. How would you computationally model a fire to capture some of these things, some of the basic inputs and parameters that would be involved? and the modeling goals and strategies of modeling a fire. Part two will then explore a particular type of way of modeling fires through computational fluid dynamics. This is a type of modeling framework that is quite detailed and follows the basic equations of motion and momentum and heat more literally than, say, a Gaussian model does, which is more parameterized. By that increased fidelity, you get more detailed ability to model a fire. And we'll show some examples of doing CFD modeling using the FDS model, which is from the National Institute of Standards and Technology in the United States. So we'll describe the model and we'll show some test runs with pool fires, which we'll define for neutral and stable atmospheric stability. In the third part of the talk, we'll then show some examples of modeling fires through the buoyant model, which is a more parameterized Gaussian type of model that's been expanding its ability to handle fires more than a typical Gaussian model. This is a non-CFD approach, a steady-state plume model with a fire plume rise parameterization model embedded. And we'll show some test cases to explore for different setups how much of the fire plume will stay in the planetary boundary layer, to kind of answer this kind of question back here of trying to model a fire that ejects a lot into the boundary layer potentially. Okay. So let's start with the background now. Okay, so these are another two pictures of large industrial fires. And just to kind of say, these things are quite common. I guess didn't get a chance to meet the participants and where they're from. But I think everyone has had some experience on the news, seeing news stories of fires in warehouses, chemical facilities, other industrial facilities that can be quite sudden and very visually scary and impressive in how big they are and how violent they kind of appear. And I don't remember exactly where these fires occurred, but somewhere in the United States. And you can kind of see a few things that will point out from looking at these photos. First of all, the heat and mass fluxes are quite large in fires compared to maybe what comes from a single smokestack. You can kind of visually see that. The heat and mass are kind of combined together into a variable called buoyancy. And that is, if you take the heat release rate per unit area, say, from this fire, and multiply it by the area of release to kind of get a sense of the mass and the scale, you get something called the buoyancy flux. And the more heat, the more buoyancy, the larger the area, the more buoyancy flux. So the more heat and mass, the more of this flux. That is the key parameter that determines how fast the plume rises and how far it will extend in the atmosphere. So this feeds into terms called plume rise, plume buoyancy, and this term clean air entrainment. That is what happens after the plume rises, how much of the air from outside the plume gets entrained into the fire plume and will mix out the heat and therefore work to decrease the buoyancy as it rises. That's another important consideration in modeling fires. Why do we model fires? Well, we want to see the dynamics, but these embedded into these fires are lots of chemicals of concern: carbon dioxide, smoke, trace metals, and others. And depending on the what is considered, any number of these things can be a problem. And we want to assess the degree of problem, say in an accidental fire, to see how much air pollution smoke blew downwind, for example, how much trace metals are embedded in there. If you're more of a climate modeling consideration, you might be concerned about how much carbon dioxide and other chemicals that are greenhouse gases might get emitted, not just from a single fire, but maybe a lot of fires, if in that case. Okay, and the other consideration with large industrial fires I pointed out is the plume rise through the atmospheric boundary layer and the penetration into the capping inversion. If the plume rises into the boundary layer, the ground level impact is heavily reduced. And that's whether it rises to that level or not is a question that one may ask and want to model. Okay, So in modeling fires, this is a diagram in a paper from Kukkonen et al. 2022, and this is the developer of the buoyant model, which we'll show some examples of simulations for towards the end of this talk. But they divide their model into a source term, a buoyant plume, in which the plume from the fire is hot enough where the entrainment of air from outside the fire isn't sufficient to kill the buoyancy. Eventually, the entrainment does kill the buoyancy, and you might get a plume that has passive atmospheric dispersion unaffected by the heat within the plume itself. So in a fire, this buoyant plume can be quite large, and therefore special treatments in a fire model would have to be made to capture that part compared to a Gaussian model, which, oops, let me go back. I think I might have accidentally hit a slide. Sorry, 1 second. There. Okay, let's go back. Here we go. Okay, so this is a diagram of maybe what a fire plume would be broken down towards in terms of modeling strategy. The steady state Gaussian plume, I think in some of your earlier talks that Paolo or others may have given, they described the Gaussian plume model. And this is the typical modeling framework for air quality from industrial smokestacks that is applied, where it's similar, where you have a plume coming from a stack eventually reaching ambient conditions and advecting downwind with the wind speed. The difference is in a typical Gaussian plume or from an industrial stack, this area where there's still momentum from the stack itself being retained is not as extensive as you would see with a fire, because the amount of heat and mass release is much less, and therefore the ambient air entrainment can bring it to ambient conditions more quickly. So some of the things, the plume rise is delta H. That's the how much the plume rises above the release height before it reaches kind of a constant height. And so delta H is what's modeled in, say, a plume rise calculation. And for Gaussian plumes, they have weak to modest plume rise. With a fire, might have very large plume rise. And this, the plume rise in a Gaussian model is calculated relatively accurately by standard Briggs plume rise equations that were developed in the late 60s and early 70s from some of the Tennessee Valley experiments during that time and other tracer experiments. So just to kind of give a little bit more equation meat to this, so you can kind of compare this. We won't go through this in detail. I pulled this from Wikipedia, which you can hit and see some of the background of the Briggs plume rise formulations. But depending on F is this buoyancy flux parameter that I talked about. It counts for how much heat and mass is released at the exit, at the release point. So this has units of meters fourth to second cubed, and it's like a measure of mass and heat flux. Depending on how big F is, the plume rise branches off into different directions, different equations, and then further branches off depending on if you have highly atmospheric stable conditions or not highly atmospheric stable conditions. Eventually, depending on the situations, you might calculate the plume rise, this delta H, with a certain equation, which I've pulled out an example of in red here and written out one of these equations. And you can see the plume rise depends on the buoyancy flux. It's inversely proportional to the wind speed. So the faster the wind, the lower the plume rise. It's kind of a measure of the faster the wind, the more quickly ambient air can get into the plume. And F is to the 1/3 power. So the bigger F, the bigger the plume rise. And the plume rise increases downwind as X to the 2/3. So this is just to kind of take that X to the 2/3 and map it back to this dotted line. You can kind of see how that might be eventually equilibrating to a final plume rise. Okay, so that's just kind of background on plume rise. Now, when you there's no like fire plume rise equation like we're showing here that I can kind of compare this to, but just to kind of give you a sense how this buoyancy flux parameter F then factors in to actual calculations for plume rise, and the Gaussian Briggs equations are an example of that. But kind of following this F parameter for fire modeling, I'm just going to take a look at the time here. Okay. get going. Um, we might we got to calculate the heat and mass release rate from the fire in terms of its the mass of fuel that's released at the fire site times the heat of combustion of the material in the fire. So you need to know how much and what's burned. And also secondarily in some equations, the organization of the fuel within the fire. That's not expressed here in this equation, but that would also be a consideration. But if you multiply the heat of combustion by the mass fuel rate, you'll get something called the heat release rate in kilowatts, which then you use to calculate the buoyancy flux. So it's the same kind of idea. You want to know how much heat and mass is released, but you do need to know what is burned and the heat of combustion of those things. Kind of give an example of what the things, the values of heat of combustion and mass release rates that happen in certain types of fires. This is, for example, for a pool fire, where for various materials, a pool fire is, you can imagine, like a ring, a metal ring that contains some kind of liquid fuel. They do these in experiments of fires, pool fires, to get kind of experimental data. And so if you can contain a liquid petroleum fuel, they for different types of fuels, they know what the heat of combustions are, and experimentally have determined what the mass combustion rate, release rate of that fuel is. So you can actually look up some numbers and calculate a value for F for certain conditions. And we'll do that in the modeling exercise where I'll show some examples of a fuel fire. Also, some things that are known are yield rates of various components like carbon monoxide, carbon dioxide, hydrocarbons, and smoke, if you want to calculate that along with the fire. And so this is a table from the same reference, Kekkonen. So that's for a pool fire. So fire modeling, basic inputs and parameters, and this is for any model. You might want to know some meteorological conditions so you can input that. You need to know the wind speed, the atmospheric stability, the boundary layer depth and the height of the inversion base, atmospheric lapse rate above the boundary layer, depending on if it's highly stable above the inversion, that's going to have an impact versus if it's not. If you're interested in particle formation in chemistry, you might want to know about the humidity and precipitation. So the same meteorological information would factor into a fire modeling application. Some desired features of fire dispersion modeling. Simple but effective inputs to characterize source characteristics. So fires are very complex, and you can, if you really want to get into the details of the pyrolysis and combustion, you can have very elaborate models, and a lot of these are options in various fire models that are out there, depending on how the user wants to configure the inputs. But a lot of times it's not possible to run those more complex characterizations because we just don't know the information. So with practical application, you want a more simple way oftentimes to characterize the fire itself, how much mass and heat is released, and the constituents. So that's why things like pool fires are useful, because they're very simple in their geometry. So proper handling of plume rise, if you can characterize the fire at the source, then this idea of how do you handle fire plume rise versus normal plume rise, the enhanced buoyancy of the fire, the entrainment of ambient air into the rising fire plume, and the CFD, which is this model will show in a second, the computational fluid dynamics approach, directly simulates plume plume rise, whereas plume models like Gaussian plume rise must parameterize that through approximations. Okay, so we'll kind of see the distinction. We look at the examples between the CFD model results and the non-CFD model results. And another thing is fires, if they're hot enough, induce their own circulations. If you imagine a hot plume rising, that hot plume, the rising air might induce, if it's hot enough, secondary circulations that are superimposed on the ambient wind speed and the ambient wind field. So when we look at some CFD animations, you'll see some of these fire-induced circulations that affect the dispersion of materials from fires. Okay, so these two approaches, which we'll show, and I'll just kind of go through this quickly so we can look at some results. Computational fluid dynamics versus a Gaussian dispersion model. The CFD model that we'll look at some results for is something called the Fire Dynamics Simulator, FDS, developed by the National Institute of Standards and Technology. It's a full 3D, it's a model based on the full 3D solutions of the Navier-Stokes equations, full suite of embedded models for fire physical processes, pyrolysis, combustion, phase change, chemistry. So we chose in the examples we'll show in a second, we chose a pool fire setup, which is probably the simplest way to set up this model. But if you really want to model like a warehouse fire or like a compartment fire, there's much more detailed options available. It's for the near field computational fluid dynamics. It's a very literal type of approach in following the 3D Navier-Stokes equations. It's on a 3D grid. So that has computational cost when modeling. So it's not possible with CFD to model a very large downwind distance. So we want to apply that to the near field, maybe the nearest kilometer from the source. The second model is the Gaussian dispersion model designed for fires, Buoyant, which is there's a link for that. It's a steady state plume model with an embedded fire plume rise model. And since it's a Gaussian model, we can extend it further downwind. It's more computationally efficient. Okay. So I misses this near field for the far field just to kind of highlight that. We'll skip through that. Okay, let's look at some CFD results now using FDS. Just get a quick drink of water. Okay, so I there's when running we want to look at the results, but I also like to use this opportunity to kind of offer some technical assistance for those that might want to run FDS. These aren't models that are commonly applied, and so users might be using it for the first time. So I do like to kind of give a little background on setting it up and a little more details on it. So see, I talked about CFD. It's from the National NIST, and here's a web link for it. Yeah, so has indoor and outdoor capabilities, simulates fire generation, spread, and dispersion. Okay, and it works on a mesh. So it's since it's CFD, you have a 3D mesh. You got to specify the grid spacing in the downwind, the lateral, and the vertical direction, and you want to make sure the grid spacing is small enough to properly capture the type of fire you're simulating, but not so small as to run out of kind of computational space to model a significant downwind distance to get meaningful results. So it's kind of a compromise with always setting up grid models. Yeah, so it's installation and execution. It's a Windows executable, which is good news. So you don't have to compile a code. It has a command line interface, no GUI. So you have to kind of know set up in a text file an input file, and then enter a run command at a command line that you pull up from your Windows DOS command, or I think it might have like its own little clickable Windows kind of command line setup within the software itself. So you enter inputs a text file, and it has a complementary graphics program called SmokeView, which also has a learning curve to it. And that's the graphics you'll see in a second are from SmokeView. And I apologize, I'm not an expert on SmokeView. So some of the graphics, while I think some of it, there's some success, some things are kind of bear explaining, and we'll get to that in terms of what you're looking at with the graphics. Okay, so FDS, here's the test runs and how the grid and inputs we set up for the runs you're going to see some examples for now. The grid was had a resolution of 25 by 25 by 25 meters over a 2 by 1 by 1 kilometer domain. So if you do the math, that's 80 by 40 by 40. That runs quickly. I mean, you can set up runs that are have many more grid spacings than that. Maybe 200 by 200 by 200 is more typical for a actual application that for a project you might be working on. But these are just test runs. So I did something simple so we can kind of see some things. I set it up for a surface pool fire. The pool fire has a 150 by 150 square source area, and it's centered in somewhere in the middle of the domain, like of 200, 1,525. So centered in X and Y, in Z in the vertical direction. Wait, take that back. Let's see. Yeah, 25. Yeah, so it's 1,000 meters tall and 25 meters above the surface is where the pool is. So that's where the pool is. And so to orient that, some of the other things you have to specify in inputs: single step mixing controlled combustion. That's one of the options that for combustion. It's you can do more complicated things than that, and one can read up on the details of combustion models. We chose a fuel is propane, a heat release rate of 250 kilowatts per meter squared. Corresponds to a fuel combustion rate of 0.005 kilograms per meter squared per second. Remember, the mass combustion rate times the heat of combustion then gives us the heat release rate. And 10% of the reactants are assumed to be smoke. So these are the things that you set up in the model. Wind meteorological inputs, background wind flow of 2 meters per second. And we did test runs for a neutral case with no atmospheric stability, adiabatic conditions, stability class D in the Pascal-Gifford classification, and stable case with the lapse rate isothermal, which corresponds to E or F depending on the wind speed. And we'll look at some comparisons of how this fire from this pool is simulated by FTS for these neutral versus stable cases. Okay, and so I won't just what it's saying is, so there is a spin up time that's required in CFD to get the flow field in equilibrium. So the fire gets turned on. The total simulation time is 4 hours, and I'm turning on the fire halfway into that simulation time. So when you look at the animations, it's going to kind of do nothing for a while, and then the fire will start. Okay, so okay, so this is for the neutral case, a snapshot of the smoke and temperature field from the fire. And so the CFD models not just the wind and the advection of the smoke, it simulates the heat itself. So you can see the temperature field, the wind field, and the smoke field, all of these. So we're not looking at the wind field here, but you do see the temperature field. So it does the model the actual heat at the fire bed getting up to close to 100 Celsius, and then cooling as the fire rises into the atmosphere. So you can see the detrainment of heat as you go upwards into the fire plume as the cleaner air advects into the fire. And in this case, since there's no atmospheric stability, the plume just keeps rising and rising and passes through the top of the domain. This is an artificial domain because this is just the smoke view graphics program kind of puts that there. But you can imagine that this is just continuing out into the atmosphere above this artificial top that's kind of being showed there. So that's for the neutral case. Let's look at an animation now of the fire plume as it's simulated. Let me just kind of, okay. Okay, so and we'll just kind of watch it for a while. So you see the CFD model is able to capture these billows because it's directly simulating the induced flows from the fire into the air. And these little billows are from the fire itself. And then the wind is going from left to right across the screen and kind of bending the plume gradually from left to right across the screen. And you can kind of see the smoke going out to the domain. So we'll let this kind of finish up. Also, you can kind of see, if you're interested in the ground level impacts, you see the shearing off of a certain amount of smoke outside the plume and kind of being detrained out of the plume towards ground level. It's not so visual compared to the smoke itself in the body of the plume, but you can kind of see how that shearing off of smoke on the edges is what's going to cause the ground level impact. Okay. Whoops, it's gonna stop this. Okay. So also, okay, that's the video. Then you saw the flow itself, and this is a snapshot of the flow vectors superimposed on the black smoke itself. And the CFD model captures the strong upward motion from the heat from the fire driving the plume upward in these big shooty arrows kind of going up and out of the image vertically. Along the edges, you see how the flow is impacted, and gradually as you move away from the fire, approaches more ambient left to right flow as you see upwind of the fire. But see, this is the strength of CFD, is that the fire itself actively affects the flow, and you can see that clearly with these flow vectors for this particular time snapshot. Okay, so let's compare that to the stable case, and we'll see some very different kind of characterization. Now, in neutral stability, the atmosphere doesn't have any effect on the buoyancy itself because there's no atmospheric stability. In stable conditions, the air temperature is isothermal in this example, which produces a inhibition of vertical motion due to the atmospheric stability that the fire is rising into. So you'll see that causes the flow behavior within the fire and the plume motion to be different. And you can see in the snapshot, we get the same thing where heat is being ejected out of the fire, and the heat is being reduced as it goes upwards. But you see as the plume is going upwards, it's encountering positive stability, and that's causing different kind of motions to occur, and not just this straight up and out thing that we saw in the neutral case. So let's kind of see how an image like this might be generated through the animation itself. So let's look at an animation for the stable case now. And so here it comes. And you see at this point, the plume is not so much going up and out, but it's hitting the positive stability, and the momentum is dying quicker, and it's being advected left to right out the side of the domain in this case. You see a lot of the same billowing effects. And you also see that a lot of the plume mass, it's not going up and out, but it's also being captured aloft, not mixing down as much. So it's kind of this plume captured within the stable air above ground level and going out the right of the domain. So stability is a very important input to plume models. And you see, you get very different plume behavior depending on if it's stable or neutral. Okay. So, oops, go back. All right, so here is a snapshot, like we saw with neutral, of a particular time during the animation for the fire plume in the stable case. And you see we get the rising of air into the fire, some of it going out, but a lot of it being, trapped in the stable air and advecting outwards. You can kind of see a very interesting counter circulation being generated by the fire and its interaction with the stable atmosphere. You kind of see at least aloft, a kind of a clockwise type of motion moving plume clockwise into kind of this eddy formation. And then the shearing off of the velocity on the edge of the plume kind of to more a left to right motion. So this is a very complex type of motion that's being captured here. And it's kind of keeping smoke kind of wafting around in the upper atmosphere, the upper boundary layer rather. And there's That's very distinct from the neutral case where it just goes up and out. So yeah, just to kind of, this is smoke visuals at T equals 2 hours after the fire starts. 1,000 meters is this top. And this, remember, this is an artificial top. This isn't a actual physical surface. But neutral case kind of just goes vertically up and out. And then in the stable case, it gets kind of trapped here. So notice they're shearing off of some plume mass, and some of that mixes to the surface. And that's something that we might be interested in knowing how much mixes the surface if we want to actually interested in ground level impact where people live, for example. And this is overlaid with temperature, just to kind of emphasize that point here. Okay. Flow vectors at T equals 2 hours after the fire start kind of highlights some of the, in both cases, these secondary circulations from due to the fire that get induced that the CFD captures, and the differences between how those are, how those develop between neutral and stable. And again, down here, this is the the square pool. That's the source of the fire down there. Okay. Here is a, if you know, to kind of quantify how much PM 2.5. So one of the things that was input into the is the smoke yield, and I don't I can't remember how I got to up 2.5 out of that, but that maybe I think there was a for smoke there's a percentage of how much of that is PM 2.5 that I applied to get this number. Can't remember the details, but in any case, the neutral case is on the left, the stable case is on the right, and these are these different dots are for different distances downwind of the fire. So X equals 150 meters for blue, for orange, X equals 400 meters downwind of the fire source, and for gray, 650. So for you can see as you go further downwind, and this is going vertically. So the vertical axis is vertically up the fire. So it's PM 2.5 on the horizontal, vertical is the height of the plume. So as you go upward in the plume, you go more and more into the plume mass, and you see higher concentrations. As you go downwind, the concentration decreases as you go downwind. So it's you get up to 4,000 micrograms per meter cubed at X equals 150 in the body of the plume. And then that decreases as you go downwind. And as you go closer to the surface, you get less and less plume because it's more aloft. And so if for the stable case, remember more of the plume got trapped in the boundary layer. So you see more plume downwind at these heights than in the neutral case where it winches up and out of the domain. So we can also look at the ground level concentration comparison for different distances downwind, 0 being where the source is, and going down 500, 600, 700 meters, PM 2.5 on the horizontal, on the vertical. And it actually turns out, interestingly enough, that the neutral case had slightly more PM 2.5 at ground level than the stable case, even though a lot more of the mass of fire stayed in the boundary layer in the stable case, not as much of that mixed to the surface, evidently. And in the neutral case, more of that mass got sheared off and did find its way to the surface. But you can see that compared to going back, the thousands of micrograms per meter cubed that are in the body of the plume itself, what's actually getting to the surface can be orders of magnitude less than that. And this is why fires are very complex, and it's very important to properly model fire, because there is this very big gradient of concentrations over the domain because of the complexity of the way fires work. Okay, so Paolo, we're at a minute 47. I think I can wrap this up in like 5 minutes, 10 minutes, if that's enough time, or you think we want to just stick with the CFD? What do you think?
Sorry, you had 50 minutes, so from the beginning, so you can talk for 10 minutes for sure.
Okay, good. I just wanted to make sure that what you felt. I think we got enough time for this. So, okay. So the part three, we're going to look at now, get away from the CFD modeling and talk about a Gaussian plume model that's been adapted for fires, and it's called Buoyant, and it got developed by the Finnish Meteorological Institute. So CFD, remember, it's for the area very close to the fire, and so you wouldn't apply it for far downwind distances. So there is an interest in adapting a Gaussian model for those applications. So let's go. And yeah, that's what I'm emphasizing here is the near field so the far field would be the Gaussian. This is where you would want to you have models for this transition of the buoyant plume into a Gaussian plume and kind of capture the full range of possibilities over a longer downwind distance compared to a CFD, which is more focused on the fire plume itself. So Buoyant is the name of the model, and here's some background on that model. It's from the Finnish Meteorological Institute. There's a link here to that, and I'll share these slides after the meeting so you guys can click on these links if interested. Steady state Gaussian plume model with an embedded fire plume rise model for far field dispersion greater than 1 kilometer. A little bit notes on the installation and execution of Buoyant. This is a Fortran code, so you do need to compile the code into a binary executable. So the user would need to install a Fortran compiler. I've given what I did was, if you install a Linux virtual environment on a Windows machine, MSys virtual Linux, that's what I use. This has a G Fortran as a package that you can then install. So that's what I did, and to kind of adapt my Windows machine both for the Linux virtual environment and a Fortran. And there's a command line interface, no GUI like the FDS model. And you enter inputs in a text file, and you get a text file outputs. So and then I've just started to run this model, so I don't have getting used to the output files and how to pull that into graphics programs is something I'm just learning. But I did able to understand enough to show some comparative results that I'll show now. So the question that we're going to do some parametric studies with this model try to answer this question I alluded to in the beginning with large industrial fires is how much of the plume stays in the boundary layer for a large fire. So you can see this is an example of a large fire somewhere. I don't remember where, but the fire was hot enough so it rose and rose and rose and penetrated above the boundary layer. Once it gets above the boundary layer, it's very plume mass will travel very long distances without hitting the surface in general. And so the question of when and what conditions a fire would rise above the boundary layer versus when it won't, and how much of the mass is above the boundary layer versus how much doesn't stay in the boundary layer is an important question that we wanted to explore in modeling. And this Buoyant model provided a platform to do that. And I'll show you some run cases to check how the model predicts this quantity. Okay, so the meteorological inputs for the Buoyant runs were a wind speed of 3.22 meters per second. I think I chose that because there was a test case that was provided with the model that I started with, and that was the wind speed they used, and I just adapted it from there. So a wind speed of 3.22, a neutral atmospheric boundary layer with depth of 1,000 meters. So what that means is that there's an inversion top at 1,000 meters. Okay, and then there's a pool fire setup as we've had with the FDS case with the CFD, where I chose a low heat release case, a medium heat release case, and a high heat release case, ranging from 2,700 to 1,800 kilowatts per meter squared. So the hotter the fire, the more likely to rise above the boundary layer. The lower the heat release, the less likely it will be. And that's the anticipated results, but what's the actual numbers in terms of quantity of mass above the boundary layer top. Just as a reminder to kind of reconcile this with our FDS case, and I just put in red here, the heat release rate for the FDS case, those animations we saw, was 250 kilowatts per meter squared. So 250 puts that case between case 1 and case 2. So just to kind of get some context with what we saw before. Okay. So here is, I'm trying to, I think I chose an isothermal stable layer above the boundary layer top. I'm trying to remember, but so there's a boundary layer top at 1,000 meters and a heat release rate of various amounts. And so one thing that's able to be gotten out of one of the output file lines in the output files is the fraction of plume that stays in the atmospheric boundary layer. So it explicitly calculates that as an output and reports that to you in the output file. So that's why it's real handy to kind of do this test case. So for the case 1 to case 2, case 3, on the far right column is the fraction of plume in the boundary layer. And for case 1, we got like 56%, 0.5597. So about half the plume was in the boundary layer, half got above the boundary layer for the 20 kilowatts per meter squared. When we increased that to 700, about 20% of it stayed in the boundary layer and 80% was above the boundary layer. When you went to 1,800 kilowatts per meter squared, only 5% of the mass stayed in the boundary layer. So you see that knowing how to get the heat release rate from the fire, what is the fire made of? What's the heat of combustion in the materials in the fire? How is the material stacked in the fire? So does it burn hot or does it burn cold? These are the key things to know in trying to do a practical application of a fire, because depending on getting that right or wrong is going to make a big difference in how much of the plume stays in the boundary layer and how much will then hit the surface. So fraction in the ABL is highly sensitive to fire strength. And so this makes knowledge of how to characterize the source of a fire the key thing, and that's one of the more difficult things. And so we're exploring ways of knowing that is going to be very case dependent, and we're also seeing if there's data sets out there that can kind of give some back of the envelope kind of back. In absence of any other information, what could we use? So we're doing a literature search now to kind of better understand how to characterize the source of a fire because it's so sensitive to the output. So the more plume in the boundary layer, the higher the surface concentration, the less plume in the boundary layer, the lower the surface concentration. And it appears these outputs from this point model do appear to capture an observable feature of strong fires, that most of the plume mass can stay aloft above the boundary layer, as we kind of see here in this photograph of a large fire. So conclusions, dispersion modeling for fires, 2 approaches were demonstrated as alternatives to typical Gaussian models. One was the computational fluid dynamics approach, the FDS model is what we showed. And the second is the steady state Gaussian modeling for fire plume rise with a fire plume rise modification in it and that model is called buoyant. The 2 approaches demonstrate as alternatives to Gaussian models. Initial test results of both appear promising. And so the next steps are to find some actual data and do some actual kind of more detailed comparisons and studies. But this kind of getting our feet wet approach and looking at the behavior itself and reconciling it with what we kind of observe from photographs is an important first step. And I feel like, at least from our initial runs with Paolo and I and my work independently, there's some level of success here that I wanted to share with you. And also encourage, if there's any interest out there in you guys needing or wanting to model fires, to provide some models as alternatives and offer our experience as someone you can consult with and learn from. So thank you guys for allowing me to talk with you today, and I'm happy to take any questions if there's time for that. Thank you again.